In 1935, a philosopher named Grete Hermann found a fatal error in the theorem physics was using to prove that Einstein's objection to quantum mechanics could never be tested. She had trained under Emmy Noether. She published it that year, and the field did not read her for 31 years, until a man at CERN found the same error and everyone behaved as though nobody had ever noticed. That is the pattern, and it does not stop. David Bohm built the theory that error had supposedly ruled out, and ended up in Brazil with his passport confiscated. John Bell published the deepest result in the foundations of physics in a journal that paid its authors instead of billing them, because he could not afford the page fees, and it went bankrupt and the money never reached him. John Clauser was warned that running the experiment would finish his career, ran it anyway, and was right. Tonight, we follow that trail. 4 pages Einstein did not write and regretted within 5 weeks. A leak to the New York Times 11 days early. Bohr producing a reply nobody since has been able to paraphrase. Telescopes pointed at quasars, borrowing randomness from light older than the sun. And a Nobel Prize handed out in 32 years after Bell was already dead. Get comfortable, stay with it, because by the end you will understand that Einstein was not the man who failed to understand quantum mechanics. He was the man who worked out exactly what it would cost and refused to pay. If you want these without ads, that is over on our Patreon, Meridian Labs, which this channel is part of, plus early access before episodes go public. Subscribe or join if you haven't. Let's ease into it. On a clear night in January of 2018, at an observatory in the Canary Islands, a team of physicists pointed 2 telescopes at 2 different quasars on opposite sides of the sky and used their light to make a decision. Not to study the quasars, not to measure them, to use them as a switch. The light from the first quasar had left its source roughly 7.8 billion years ago. The light from the second had left roughly 12.2 billion years ago, which is to say it departed when the universe was less than 2 billion years old, before the sun existed, before the earth existed, before there was any such thing as carbon in sufficient quantity to build a person who could one day look at it. Those photons crossed most of the observable universe, arrived at a mountain in the Atlantic, hit a detector, and their colour was used in real time to decide which way to turn a polarizing filter in a laboratory a few kilometers away. They did this because they needed a random number that could not have been tampered with, and they had reached the point in this argument where the only source of randomness they were willing to trust was light older than the solar system. I want you to sit with the absurdity of that for a second. Not the physics, the desperation. Somewhere along the way, a disagreement about the nature of reality escalated to the point where serious, funded, peer-reviewed scientists concluded that the only way to settle it was to reach back nearly to the beginning of time and borrow a decision from a dying galaxy. And it still did not fully close the argument. It narrowed the gap. It pushed the escape route back 7.8 billion years. It left a sliver. Everything about that experiment traces back to 4 pages published in Physical Review on the 15th of May, 1935. Volume 47, pages 777 through 780. The title is a question. Can quantum mechanical description of physical reality be considered complete? The authors are listed as Albert Einstein, Boris Podolsky, and Nathan Rosen. That paper was written to kill quantum mechanics. It is now the most cited paper Einstein ever wrote, more cited than the photoelectric effect that won him the Nobel Prize, more cited than special relativity. It is among the 10 most cited papers in the entire history of Physical Review, a journal that has been running since 1893. And the reason it is cited is not that it succeeded. It is cited because the specific scenario Einstein and his two collaborators constructed as a weapon turned out to be the most productive idea in the foundations of physics for the following 90 years. It defined entanglement. It gave Schrodinger the word. It gave Bell the target. It gave three men the Nobel Prize in 2022, 87 years later, for proving Einstein wrong using the exact machine he built to prove himself right. That is the story you have probably heard in outline. Einstein attacked, Einstein lost, entanglement is real, spooky action at a distance, isn't physics wonderful? Almost every part of that summary is wrong. Einstein did not write the paper. He did not approve the final draft. When he read it in print, he was unhappy with it, and he said so in a private letter within 5 weeks. The phrase spooky action at a distance does not appear anywhere in it, and would not exist for another 12 years. The argument the paper actually makes is not the argument almost anyone thinks it makes. And the thing Einstein was genuinely afraid of, the thing that kept him arguing about this until the last years of his life, was never refuted by Bell, was never refuted by Aspect, and has never been refuted by anyone. It was relocated, it was renamed, it was made respectable, and then it was quietly filed under the heading of things that work, and therefore do not require explanation. Here is the question I want to hold open for the next 2 hours, and I am telling you up front that I am not going to close it, because nobody has closed it. When two particles are entangled and you measure one of them, the other one behaves as though it knows. Not sometimes. Every time, to 11 decimal places of experimental agreement. Across separations of 12 meters and 1,200 kilometers, and every distance anyone has bothered to test, something is connecting them. What is it? Not what does the mathematics predict. The mathematics is not in dispute, and has not been in dispute since about 1927. Not whether the correlations are real. They are real, they have been measured to a statistical confidence that borders on the theological, and anyone still arguing about the data is arguing in bad faith. I mean the plain, stupid, physical question. Two objects, separated in space, correlated in a way that cannot be explained by anything they carried with them when they left. What is between them? Ask a physicist that question directly and watch what happens. Some of them will tell you the question is meaningless. Some will tell you it is a matter of interpretation and therefore not physics. Some will tell you nothing is between them and the correlation is simply a fact about the world with no further explanation available. A small number will tell you the truth, which is that they do not know, that nobody knows, and that the field made a collective decision 70 years ago to stop asking. Einstein asked. That is the only thing he did that was genuinely unforgivable, and the field has spent 9 decades filing his objection under the heading of an old man's failure to keep up. He was not failing to keep up. He had found the crack. He got the conclusion wrong, and he found the crack, and the crack is still there. Start with the paper, because the circumstances of its creation are so strange that they are usually left out entirely. Physical Review received the manuscript on the 25th of March, 1935. It was published on the 15th of May. 7 weeks, which even by the standards of the 1930s was fast. It was fast because it was not refereed in anything like the modern sense. Physical Review under the editorship of John Tate did not run papers past external reviewers as a matter of routine. The editor read it, judged it worth printing, and printed it. Hold on to that, because there is a bitter joke coming. The argument in the paper is short, and it is not about the uncertainty principle, whatever you may have absorbed from popular accounts. Einstein had made his peace with the uncertainty principle years earlier. He had tried to break it at the Solvay conferences in 1927 and 1930. most famously with the photon box thought experiment in 30, and Bohr had beaten him. And Einstein had accepted the loss. He was not relitigating that. The paper begins with a definition, and the definition is the entire weapon. It proposes a criterion for when we are entitled to say that something is real. If you can predict a quantity with certainty, without in any way disturbing the system you are predicting it about, then that quantity corresponds to something physically real. Something that is out there, whether or not you look. That sounds mild. It sounds like the kind of thing you would nod along to. It is one of the most consequential sentences written in the 20th century, because everything that follows is a trap built on it. The setup is two particles that interact and then separate. Because they interacted, their properties are correlated. Measure the position of the first particle, and you can compute the position of the second. Measure the momentum of the first, and you can compute the momentum of the second. You choose which one to measure. And crucially, on the assumption that your measurement here cannot affect anything over there, you have not disturbed the second particle in any way. Therefore, by the criterion, the second particle has a real position. And it also has a real momentum. Because you could have chosen either, and whichever you chose, you would have learned something about the distant particle without touching it, and something that is there to be learned without touching must have been there already. But quantum mechanics says position and momentum cannot both be definite. The mathematics forbids it. The two quantities correspond to operators that do not commute, which is the formal way of saying the theory refuses to assign them both at once. Either quantum mechanics is incomplete, or the assumption that your local action cannot reach across the gap is false. That is the whole argument. 3 moves. Define reality, construct a case where the definition applies to a distant object, show that quantum mechanics denies what the definition just established. Notice what is not in there. No claim that you can measure position and momentum simultaneously. Einstein knew you could not. No claim that quantum mechanics makes wrong predictions. He never said it did. No hidden variables. The phrase does not appear. The paper does not propose a replacement theory and does not sketch one. What it proposes is a dilemma, and Einstein was completely confident which horn any sane person would choose. Of course the theory is incomplete. The alternative is that measuring something in one place changes what is real in another place, instantaneously, with no mechanism, across any distance. That was not a serious option. That was the reductio. That was the absurdity you point at to show you have won. He put the absurd option on the table as a rhetorical device. 90 years of experiment have not been able to get it off the table. But before any of that, before Bohr, before Bell, before anyone had a laboratory capable of testing a word of it, the paper went wrong in a way that made Einstein furious, and it went wrong 11 days before it was published. On the 4th of May, 1935, the New York Times ran a story on page 11. The headline read, "Einstein attacks quantum theory." The article described the argument, quoted the conclusion that the theory was correct but not complete, and told the reading public what the physics community would not see for another week and a half. Einstein had not authorized it. Einstein had not been asked. 3 days later, on the 7th of May, the Times printed his response, and the wording is worth reading slowly because it is a man in a controlled rage. Any information the article was based on, he said, was given without his authority. It was his invariable practice, he said, to discuss scientific matters only in the appropriate forum, and he deprecated advance publication of such announcements in the secular press. The word deprecate is doing a great deal of work there. In 1935, from Einstein in a newspaper that is a public execution. The leak came from inside the paper. Boris Podolsky had gone to the press, and Podolsky had done something else. he had written the entire paper. This is documented, it is not controversial among historians, and it is left out of essentially every popular retelling because it complicates the myth. The three men discussed the argument at length at the Institute for Advanced Study in Princeton. Then, Podolsky wrote it up, in English, because Einstein's written English in 1935 was still awkward and Podolsky's was fluent. And by the best available reconstruction, Einstein did not see the final draft before it was submitted. The most famous critique of quantum mechanics in history is a paper Albert Einstein did not write and did not read before publication. On the 7th of June 1935, Erwin Schrodinger wrote to him from Oxford, delighted. He said that in the paper which had just appeared in Physical Review, Einstein had publicly seized dogmatic quantum mechanics by the scruff of the neck. That is his phrase, in the letter, and you can hear the glee in it. Schrodinger had been isolated for years. He had watched the Copenhagen consensus harden around a position he thought was philosophically incoherent, and he had watched his own wave function get reinterpreted out from under him. Somebody had finally hit back, and it was the one man with enough authority to survive doing it. Einstein wrote back on the 19th of June. The letter is catalogued in the Einstein archive as document 22-047, and it contains the sentence that reframes the entire episode. For reasons of language, he said, the paper was written by Podolsky after many discussions. But it had not come out as well as he had really wanted. On the contrary, the main point was, so to speak, buried by the erudition. Buried by the erudition. Smothered by the formalism. The German word is Gelehrsamkeit, which carries a faint sneer, the sense of learntness for its own sake, scholarship as decoration. 5 weeks after publication, the man whose name leads the author list is telling a colleague in private that the paper does not say what he wanted it to say, and he spent the next 14 years trying to say it properly. He rewrote the argument in 1936 in Physics and Reality, in the Journal of the Franklin Institute, where he first called it a paradox. He rewrote it in 1948 in the Dialectica paper, Quantum Mechanics and Reality in German, tightly, in about 4 pages. He rewrote it again in 1949 for the Schilp volume, Albert Einstein Philosopher-Scientist, in his reply to criticisms. Different versions, different thought experiments, boxes and balls and unstable powder kegs, over and over for the rest of his working life. You do not do that if you think your point landed. The relationship with Podolsky did not recover in any meaningful sense. Einstein regarded the leak to the Times as a serious breach, and there are accounts that they never spoke again, though I want to be careful there, because that specific claim is repeated more confidently than the documentation supports. What is documented is that the collaboration ended, that Podolsky took a position at the University of Cincinnati and later at Xavier University, and that he never again worked at the level he had briefly occupied in Princeton in the spring of 1935. There is more to Podolsky. There is a great deal more to Podolsky, and it involves a Soviet codename and a meeting in an embassy in 1943, and I am going to come back to it, because it is the strangest single item in this entire story, and I do not want to introduce it casually. There is also something else that happened in 1935 that almost nobody connects to this. The same year, the same journal, one of the same 3 men. Einstein and Rosen published a second paper in Physical Review, volume 48, pages 73 to 77, on the 1st of July, 6 weeks after the entanglement paper. It described a structure in general relativity that connects 2 distant regions of space through a throat. A bridge. It is where the word wormhole eventually comes from. 2 papers. 1 year. 1 journal. 1 shared author. One of them says that two distant things cannot secretly influence each other. The other one describes a tunnel between two distant places. Remember that. 78 years later, two physicists are going to propose that those two papers are describing the same thing, and when they do it, is going to feel less like a discovery than like a punchline that took most of a century to arrive. But in the summer of 1935, nobody was thinking about wormholes. In the summer of 1935, the entire architecture of quantum mechanics was under attack by its most famous living critic. And the man who had built that architecture was 300 kilometers away in Copenhagen, having what those around him described as something close to a breakdown. Leon Rosenfeld was working with Bohr when the news arrived. His account is the one everybody quotes, and it deserves to be quoted properly. The attack came down on them, he wrote, as a bolt from the blue. The effect on Bohr was remarkable. As soon as Bohr had heard the summary of Einstein's argument, everything else was abandoned. Everything else was abandoned. Bohr stopped work on the paper he was writing, he stopped work on everything. And for roughly 6 weeks, in the summer of 1935, the most influential figure in physics dictated, redictated, tore up, and started again on a response to 4 pages he could not immediately answer. Rosenfeld also recorded something that tells you more about the emotional temperature than any of the physics does. Bawl, pacing, muttering, working the names over. Podolsky, Opodolsky, Iopodolsky, Siopodolsky, a nonsense chain, building on the name of the junior author, the one it was safe to be angry at. He could not attack Einstein directly. Einstein was Einstein. But Podolsky was a nobody. Podolsky had leaked to the newspapers, and Podolsky's name could be turned into a childish little song by a 50-year-old Nobel laureate who was frightened. Because he was frightened, that is the part the standard account smooths over. Bohr was not serenely confident and waiting for the right moment. His closest collaborator described the arrival of the argument as a bolt from the blue, and the response as the abandonment of all other work for 6 weeks. That is not what confidence looks like. That is what it looks like when someone shows you a hole in your foundation. What Bohr eventually produced, and this is where I need you to pay close attention, is one of the most consequential and least comprehensible documents in the history of science. It arrived at Physical Review on the 13th of July, 1935, and was published on the 15th of October in Volume 48, pages 696 to 702. Bohr gave it the identical title. Word for word, the same question Einstein had asked. Can quantum mechanical description of physical reality be considered complete? It is a deliberate act of dominance, the intellectual equivalent of repeating someone's sentence back to them in the same tone. And the argument inside it is, by wide agreement among people who have spent careers reading it, unclear, Bohr concedes the crucial point immediately. He accepts that measuring the first particle causes no mechanical disturbance to the second. There is no force, no kick, no signal, nothing propagating across the gap. He grants it. Then he says that there is nevertheless an influence on the very conditions which define the possible types of predictions regarding the future behavior of the system. Read that again, an influence on the conditions which define the possible types of predictions. What is a condition that defines a type of prediction? Where is it located? Does it exist in the second laboratory, or does it exist in some abstract space of possible experimental arrangements? Is it physical? Can it be measured? Does it propagate? If it does not propagate, in what sense was it influenced? Bohr does not say. Bohr never says, not in this paper, not in the 15 years of follow-up writing he produced on the same subject. His own abstract states that the EPR criterion of reality contains an essential ambiguity when applied to quantum phenomena, That is the counterattack. The definition of reality is ambiguous. I have read this reply more times than is healthy, and I want to be straight with you about my own position, because pretending to neutrality here would be dishonest. I do not think Bohr answered the argument. I think he asserted with enormous personal authority that the argument rested on a concept of reality that was not applicable, and that the physics community, which desperately wanted the problem to go away, accepted the assertion because it came from him, and because accepting it meant they could go back to work. I am not alone in that. Marabella's Quantum Dialogue, which is the most detailed scholarly reconstruction of the rhetoric of the Copenhagen school that exists, treats the reply as strategically vague. Arthur Fine, in The Shaky Game, treats it as a failure to engage. Don Howard has spent a career documenting how thoroughly the reply misses what Einstein was actually worried about. And John Bell, who thought about this harder than anyone alive, dismissed Bohr's reply outright in interviews. When asked what Bohr's answer to EPR was, his response amounted to a shrug at an argument that never arrived. Here is a fact about the aftermath that should bother you more than it seems to bother the textbooks. Bohr's reply was published in October of 1935. It was accepted as decisive almost immediately. Within a couple of years, the standard position across the discipline was that Einstein had been answered, that the matter was closed, and that anyone still asking about it was displaying a lack of professional seriousness. Nobody could say what the answer was. But everybody agreed the answer had been given. That pattern, the answer that everyone accepts and nobody can state, is going to repeat in this story until it stops looking like an accident. But if Bohr misunderstood the argument, the obvious question is what the argument actually was. And to get at that, you have to stop reading the paper Podolsky wrote and start reading the letters Einstein wrote, because they are not saying the same thing. The version that gets handed down is that Einstein could not accept randomness. God does not play dice. The stubborn old determinist, unable to let go of a clockwork universe, embarrassing himself in public while the young men built the future without him. The dice line is real. It comes from a letter to Max Born dated the 4th of December 1926, and the full passage is more interesting than the fragment. Quantum mechanics, he wrote, is very impressive, but an inner voice tells him it is not yet the real thing. The theory produces a good deal, but hardly brings us closer to the secret of the old one. He is at all events convinced that he does not play dice. 1926. That is 9 years before EPR, written when the theory was months old, and it is a statement about incompleteness, not about randomness as such. Not yet the real thing, does not bring us closer. By 1935, Einstein's objection had moved somewhere much more specific and much harder to dismiss. Don Howard's work in the mid-1980s, and Arthur Fine's before it, established this from the correspondence, and it is now the mainstream scholarly reading, even though it has never made it into the popular story. Einstein's target was not indeterminism. It was not the uncertainty principle. It was two assumptions so basic that physics had never previously bothered to give them names, and which he insisted had to be separated from each other. The first is separability. Two systems that are spatially separated have their own independent states. There is a fact about what is going on over here and a different fact about what is going on over there, and the total situation is the sum of the two. The second is locality. What you do here cannot instantaneously change what is true there. Einstein believed both. He believed the first one more than the second, which is not the way anyone tells this story. His argument in the Dialectica paper of 1948 is not primarily about influences travelling faster than light. It is about whether it makes sense to talk about distinct objects at all. If two things separated by a distance do not have their own separate states, then the whole idea of a physical object as a thing in a place becomes untenable And if that goes, then physics as an enterprise, the business of describing what is where, has nothing left to describe. That is what he was defending. Not determinism, not classical mechanics, the proposition that things exist separately in places. He was quite explicit that if you give that up, you are not adjusting a theory, you are abandoning the possibility of theory. And here is the first thing you were never told about the most famous phrase in this entire subject. Spooky action at a distance does not appear in the EPR paper, not in those words, not in translation, not as a concept described in other language. Go and read the 4 pages. It is not there. The phrase comes from a letter Einstein wrote to Max Born on the 3rd of March, 1947, 12 years after EPR. It is in the published Born-Einstein correspondence, and the context is not an attack on entanglement specifically, but a broader statement about what he requires of a physical theory. He cannot seriously believe in quantum mechanics, he says, because it cannot be reconciled with the idea that physics should represent a reality in space and time, free from spooky actions at a distance. The German is spukhafte Fernwirkung. Spukhafte is closer to ghostly than to spooky. Spooky in English in 1947 was a slightly ridiculous word, and the translation has given the phrase a whimsy it does not have in the original. Ghostly remote action. Action by a haunting. 12 years after the paper. In a private letter, about a general philosophical requirement, that phrase is now printed on the cover of popular physics books, attributed to a paper it is not in, describing a phenomenon Einstein was arguing does not exist. While I am here, the other famous one. Is the moon there when nobody looks? Einstein did not write that. It appears in a memoir by Abraham Peiss, in Reviews of Modern Physics, Volume 51, in 1979, recalling a walk the two of them took in Princeton, during which Einstein asked him whether he really believed the moon exists, only when someone is looking at it. Peiss is recalling a conversation, decades later, and reporting it in his own words. It is a real recollection from a serious historian who knew him well. It is not a quotation. None of this is trivia. It matters because the way you remember an argument determines whether you think it was answered. If you think Einstein's complaint was about dice, then Bell settled it and Einstein was a stubborn old man. If you understand that his complaint was that separated things must have separate states, then what happened next is much worse for everybody, because that assumption was not defended by anyone. It was executed. And the field has been living in the world after that execution ever since, without ever quite saying so out loud. Schrodinger understood it. He understood it faster and more clearly than anyone else alive, and what he did with it in the 6 months after the paper appeared is the single most productive response to a piece of scientific criticism I know of. He picked up the thing Einstein was pointing at and gave it a name. The paper is Discussion of Probability Relations Between Separated Systems. In the Proceedings of the Cambridge Philosophical Society, Volume 31, pages 555 to 563, 1935, communicated to the Society by Max Born. In it, Schrodinger coins the English word entanglement and the German word Verschränkung, which literally describes crossed or folded arms, limbs interlocked, a thing you cannot separate without breaking the position. And he says something in that paper which is quoted constantly and understood rarely. When two systems interact and then separate, he writes, they can no longer be described the way they were before, and he refuses to call this one of the characteristic traits of quantum mechanics. He calls it the characteristic trait, the one that enforces the theory's entire departure from classical lines of thought. Not a strange feature, the strange feature. The single thing that makes the theory different in kind rather than in degree. Read that against Einstein's letter of 6 months earlier, and you get the shape of what happened. Einstein constructed entanglement as a demonstration that quantum mechanics could not be a complete description of reality. Schrodinger read the same construction and concluded that entanglement was the deepest true thing quantum mechanics had to say. Same scenario. Same mathematics. Opposite verdicts. And they agreed with each other about almost everything else, corresponded warmly for years, and were both, in the terms of the profession at that moment, losing. In November of 1935, Schrodinger published a long article in Nanoseconds called The Present Situation in Quantum Mechanics, and in section 5 of that article, almost in passing, he put a cat in a box. Everyone knows the cat. Almost nobody knows what it was for. The cat is not an illustration of how wonderfully strange quantum mechanics is. The cat is a weapon. Schrodinger constructed it to demonstrate that the standard interpretation, taken at its word, produced an absurdity. If a quantum system in superposition is coupled to a large system, and the theory says the quantum system has no definite state until measured, then the large system has no definite state either, and you get a cat that is neither alive nor dead. He thought this was ridiculous. He said so. He called the resulting situation, in the article, a burlesque. 90 years later, that burlesque is printed on t-shirts and used as an example of how mysterious and beautiful the quantum world is. The demonstration of absurdity became the mascot. And the cat did not come from nowhere. Einstein sent Schrodinger a letter on the 8th of August, 1935, 3 months before the Nanoseconds article, describing an unstable pile of gunpowder, a charge that may or may not have ignited within a certain time. According to the theory, after that time, the description of the system is a superposition of exploded and not exploded, which Einstein regarded as obviously unacceptable as a description of an actual pile of gunpowder in an actual room. Schrodinger swapped the gunpowder for a cat, added a flask of acid and a Geiger counter, and made the point unforgettable. 2 men, both losing an argument, corresponding across an ocean in the summer of 1935, inventing between them the 2 most famous images in modern physics, entanglement and the cat, both of them intended as demolitions, both of them now taught as celebrations. There is a pattern here, and it has nothing to do with the quality of the physics. Then the argument stopped, not resolved. Stopped. From 1935 to 1952, 17 years, essentially nothing happened on this question. From 1935 to 1964, 29 years, nothing happened that changed anything. The most cited paper Einstein ever wrote sat there, uncontested and unexplored, for the better part of 3 decades. Part of that is the war. It is difficult to overstate what happened to theoretical physics between 1939 and 1945. The field emptied into weapons work. The men who might have spent the 1940s worrying about the ontology of separated systems spent it calculating neutron cross-sections and implosion geometries. The people who came out the other side had learned something about their discipline that they did not unlearn, which is that quantum mechanics works, that it works with terrifying precision, and that nobody needed to understand what it meant in order to level a city with it. The other part is a change in the culture of the profession, and this one deserves to be named exactly. The attitude eventually got a slogan: shut up and calculate. You have heard it attributed to Richard Feynman, probably more than once. It is not Feynman. The phrase was coined by the physicist David Bohm in a column in Physics Today in April of 1989, and Bohm has spent years since then trying to reclaim it, partly because he is a man who likes credit for a good line, and partly because he meant it as a criticism and watched it get adopted as a creed. That is a small correction, and I bring it up because of what it reveals. The most accurate description of the intellectual culture of 20th century physics was written as an insult by a man who thought the culture was a failure, and the culture liked it so much it put it on a badge. But there was a harder reason the question stayed closed, and it was not cultural. It was mathematical. There was a proof. In 1930, 2-3 years before EPR, John von Neumann published Mathematical Foundations of Quantum Mechanics. Von Neumann was, by any reasonable accounting, the most formidable mathematical mind working in physics in that generation, and the book did something the field badly needed. It put quantum mechanics on rigorous axiomatic footing. It was the definitive treatment, and buried in it was a theorem which was universally understood to prove that no theory of hidden variables could ever reproduce the predictions of quantum mechanics. Hidden variables is the shorthand for exactly the thing Einstein wanted. Some deeper layer of description, some additional facts about the particles that the wave function does not include, which would restore definite properties and explain the correlations as ordinary bookkeeping rather than ghostly remote action. Von Neumann's theorem said that layer cannot exist, not that it had not been found, that it was mathematically impossible. That is why the question died. Not because Bohr's reply was clear, which it was not. Because there was a proof by von Neumann, and you did not argue with a proof by von Neumann. If you were a graduate student in 1945 and you asked your supervisor whether there might be some deeper theory underneath quantum mechanics, you would be told that von Neumann had settled it in 1932, and that would be the end of the conversation and possibly the end of your standing in the group. The proof was wrong. Not subtly wrong. Not wrong in some technical corner that required later mathematics to expose. Wrong in a way that a competent reader could find by working carefully through the assumptions, because one of the assumptions was doing something illegitimate. Von Neumann required that for any hidden variable state, the expectation values of observables should add linearly, even for observables that cannot be measured together. In quantum mechanics, the additivity holds as a statistical fact about ensembles. There is no reason whatsoever to demand it of individual systems with definite values, and demanding it quietly assumes precisely the thing the theorem is meant to prove. The theorem excludes hidden variable theories by requiring them to behave like quantum mechanics first. Somebody noticed this. Somebody noticed it in 1935, the same year as EPR, and published it, and was ignored for the next 30 years. Her name was Grete Hermann. She was born in Bremen in 1901. She studied at Göttingen and took her doctorate under Emmy Noether, which puts her about as close to the centre of 20th century mathematics as it is possible to stand. Noether supervised very few doctoral students. Hermann was one of them. She was also a philosopher, trained in the Neo-Kantian tradition, and her interest in quantum mechanics was not decorative. She went to Leipzig and worked in the orbit of Heisenberg and von Weizsäcker, argued with them directly, and in 1935 published a long paper called The Natural Philosophical Foundations of Quantum Mechanics in the Abhandlungen der Friesischen Schule. In it, she identifies the circularity in von Neumann's proof and states it plainly. The additivity assumption cannot be justified for hidden variable theories. The proof assumes what it sets out to demonstrate. She had found in 1935 the exact error that John Bell would independently find and publish in 1966, and which is now in every serious treatment of the subject. Nothing happened. The journal was obscure. The paper was in German. It was a philosophy publication rather than a physics one. And she was a woman writing philosophy about the foundations of a field in 1935, which meant that the men she was correcting had a menu of ways to not read her that did not require any of them to be consciously dishonest. Then, Germany did what Germany was doing. Hermann was politically active in a socialist resistance organisation, the Internationaler Sozialistischer Kampfbund, and she had to leave. Denmark, then Britain. She spent the war in exile, doing resistance work and teaching, and she never returned to foundational physics in any sustained way. After the war, she went back to Germany and spent the rest of her career in education and teacher training. She died in 1984. She was alive in 1966 when Bell published the same criticism. She was alive in 1974 when Max Jammer's book on the philosophy of quantum mechanics finally brought her paper to an English-speaking readership. She was alive through the entire vindication, and there is no evidence anyone from physics contacted her about it. I want to be careful here because there is a version of this story that flatters everyone who tells it, in which a lone woman is silenced by a patriarchal establishment, and the truth is both less cinematic and more damning. Nobody suppressed Grete Hermann. There was no committee, no rejection, no campaign. Her paper was published. It was simply, comprehensively, not read, by a profession that had already decided the question was closed and had no incentive to check. That is the more common mechanism, and it is the one that should worry you, because it does not require anybody to behave badly. It only requires that the answer everyone has agreed on is comfortable, and that checking it is somebody else's job. 31 years passed. John Bell found the same error working alone in 1963 and 64 and wrote it up in a paper called On the Problem of Hidden Variables in Quantum Mechanics. It was published in Reviews of Modern Physics, Volume 38, pages 447 to 452 in 1966. Note those dates. Written in 64, published in 66. The delay is not editorial caution. The journal lost the manuscript. Bell had moved institutions. The proofs went to an address he had left, and the paper sat in limbo for 2 years while the field carried on quoting a theorem that had been dead since 1935. Bell's own verdict on von Neumann, delivered in an interview with Omni magazine in 1988, is the least diplomatic thing I have ever read from a serious physicist about the work of another serious physicist. The proof, he said, falls apart in your hands when you actually come to grips with it. There is nothing to it. It is not just flawed, it is silly. And then, in case that had not landed, he said it was not merely false but foolish. Foolish is a devastating word to use about von Neumann. And I have to give you the other side of this, because there is one, and pretending otherwise would be exactly the kind of tidy narrative I am asking you to distrust. Over the last 15 years, a group of historians and philosophers of physics, including Jeffrey Bubb, Dennis Diex, and Klaas Landsman, have argued that Bell and Hermann both misread what von Neumann was actually claiming, that his additivity condition was more defensible in the context of his own axiomatic framework than the standard story allows, and that the reputation of the proof has been unfairly demolished. Mermin and Rudiger Schack have argued back, forcefully, in a paper whose title is a polite way of saying that even Homer nods. That argument is live. I am not going to pretend to settle it. What is not in dispute, and this is the part that matters for everything that follows, is the operational fact. For roughly 30 years, the physics community believed a theorem excluded a class of theories which that theorem did not in fact exclude. Bohmian mechanics exists. It was constructed in 1952. It reproduces every prediction of quantum mechanics, and it has hidden variables in it. Whatever von Neumann proved, he did not prove that impossible, because it is sitting there. The consequence of the error is not in doubt even if the blame is. And now I need to tell you about the man who built the theory that was not supposed to be possible, because what happened to him is the point in this story where I stop being able to describe institutional physics as merely complacent. David Bohm was born in Wilkes-Barre, Pennsylvania, in 1917, the son of a Hungarian Jewish immigrant who ran a furniture store. He did his doctorate at Berkeley under Robert Oppenheimer. His thesis work on plasma scattering was so directly relevant to the Manhattan Project that it was classified before he could defend it, and he was not permitted to read his own dissertation. Oppenheimer had to certify to the university that the work had been completed and was of doctoral standard, because the candidate could not be shown his own thesis. That is a bureaucratic absurdity in 1943. It becomes something else entirely in 1949. Bohm had been politically active at Berkeley, Communist Party involvement, or something close enough to it that the distinction did not survive contact with the House Un-American Activities Committee. In 1949, the committee subpoenaed him. He appeared, and he invoked the Fifth Amendment, and he refused to testify against his former colleagues, including Oppenheimer. That refusal cost him everything. He was indicted for contempt of Congress in late 1950. Princeton, where he was then teaching, suspended him and barred him from the campus. He was tried and acquitted in May of 1951, and then Princeton, having watched him be acquitted, declined to renew his contract anyway. Einstein wanted him as an assistant. Einstein was at the Institute for Advanced Study, in the same town, and he was interested in Bohm's work and appalled by what was happening to him. The appointment did not happen. The Institute's director at that time was Robert Oppenheimer. Bohm left the country. He went to the University of Sao Paulo in Brazil, and shortly after he arrived, officials at the United States consulate took his passport. They gave him a document allowing him to return to America and nothing else. He was 34 years old, he had been acquitted of the charge against him, and he was now unable to travel anywhere in the world except the country that had just destroyed his career. He took Brazilian citizenship because it was the only way to get a passport that worked. Doing so cost him his American one. He went from Brazil to the Technion in Israel in 1955, and from there to Bristol and eventually to Birkbeck in London, and he never held a permanent academic position in the United States again. Now hold that timeline against the physics, because they are not two stories. In 1951, in the middle of the contempt proceedings, Bohm published a textbook called Quantum Theory. It is a good textbook. It is a conventional textbook. It presents the Copenhagen interpretation clearly and sympathetically, and in the course of doing so it does something nobody had done in the 16 years since 1935. It reformulates the EPR argument. Einstein, Podolsky and Rosen had used position and momentum, continuous variables, an experimentally hopeless setup that nobody could have built in 1935 or 1951. Bohm replaced it with two particles of spin 1/2 in a singlet state, with their spins anti-correlated. Measure the spin of one along any axis, and you know the spin of the other along that axis. And it is opposite. Two outcomes instead of a continuum. Up or down. A thing you could imagine building. That reformulation is the hinge of the entire subject. Every experiment I am going to describe for the rest of this script, every Bell test from 1972 to last year, is a version of Bohm's setup and not Einstein's. The argument became testable because a man facing a contempt trial rewrote it in a textbook, and in the process of writing that clean and sympathetic account of the orthodox view, Bohm stopped believing it. He sent a copy of the book to Einstein. Einstein invited him over. What was said in that room in Princeton in 1951 is not recorded in detail, but Bohm described the conversation afterwards as the thing that convinced him the orthodox account was not sustainable. Einstein told him, in effect, that he had explained the standard view about as well as it could be explained, and that explaining it well made its inadequacy visible. Within a year, Bohm had built the theory von Neumann had proved impossible. The two papers appeared in Physical Review, Volume 85, in 1952, pages 166 to 179 and 180 to 193. A suggested interpretation of the quantum theory in terms of hidden variables, parts 1 and 2. In Bohm's theory, particles have positions. always, at every moment. There is no collapse, no observer, no moment when a possibility becomes an actuality. The wave function is real, it evolves by the Schrodinger equation exactly as in standard quantum mechanics, and it guides the particles along definite trajectories. Every prediction of quantum mechanics comes out identical. The statistics are the same because the initial positions are distributed according to the wave function and stay that way. It works. That is the thing that has to be understood about Bohmian mechanics. It is not a proposal or a sketch. It is a complete, consistent, empirically equivalent formulation of non-relativistic quantum mechanics in which particles have definite positions and nothing is ever indeterminate. And it has a price, and the price is the thing this entire script is about. Bohm's theory is explicitly, unapologetically, structurally non-local. The guiding wave for a system of two particles is not a wave in ordinary three-dimensional space. It is a wave in configuration space, and the velocity of each particle at each instant depends on the instantaneous positions of all the others, no matter how far away they are. Move a detector in Vienna, and the trajectory of a particle in Delft changes at that moment. That is not a bug in the theory that a cleverer version would remove. It is the mechanism. It is how the theory produces the correlations. Bohm did exactly what Einstein wanted. He restored definite properties, he restored determinism, he eliminated the observer, he built the deeper layer. And in order to do it, he had to sacrifice the one thing Einstein cared about most, which was that separated things have separate states and cannot reach each other. Einstein hated it. He called it too cheap in a letter to Bohr. The man had spent 17 years asking for a completion of quantum mechanics. Someone finally produced one, and it was worse than the disease. I want to flag something here that will not pay off for another hour, and I want you to hold it, because it is the shape of the whole thing. Every attempt to fix this problem, every single one, from 1952 to this year, has succeeded by giving up one thing. And every time, the thing that gets given up is the same thing. It is never randomness, and never determinism, and never the observer. It is the idea that the world is made of separate parts. You will see it happen 5 more times before we are done. Watch for it. The reception of Bohm's papers was not a debate. It was closer to an immune response. Wolfgang Pauli, who had seen a version of this idea from Louis de Broglie in 1927 and demolished it at the 5th Solvay conference, called Bohm's work artificial metaphysics. Leon Rosenfeld, Bohr's closest collaborator, the man who had written down the bolt from the blue, attacked it in terms that had nothing to do with physics. He accused Bohm of philosophical error, of regression, of a failure of nerve. The Oppenheimer line is the one everybody quotes, and I am going to give it to you with the caveat it requires. It is reported that after a meeting at Princeton at which Bohm's paper was discussed, and nobody could find a technical error in it, Oppenheimer said that if they could not disprove Bohm, then they would have to agree to ignore him. That account circulates widely. It is anecdotal. I have not been able to trace it to a contemporaneous document, and you should treat it as a story physicists tell about themselves rather than as a minuted quotation. But notice that they tell it. Notice that this is the story the profession has chosen to preserve about its own conduct in 1952. Nobody repeats that line as an accusation. It gets repeated with a kind of rueful admiration. And whether or not Oppenheimer said the words, the policy described is precisely what was implemented. Bohm's theory was not refuted. There is no paper refuting it. There is no experiment ruling it out. It survives to this day. It is taught in a handful of departments. It has a small and serious literature, and for roughly 40 years the standard practice in graduate education was not to mention that it exists. Not because it was wrong, because it was inconvenient. I said earlier that the pattern would stop looking like an accident. Count with me, de Broglie proposes a pilot wave in 1927 and is humiliated at Solvay and abandons it. Grete Hermann finds the flaw in the impossibility proof in 1935 and is not read. Einstein constructs the sharpest objection anyone has ever made, and it is declared answered by a reply nobody can paraphrase. Bohm builds the impossible theory in 1952 and is exiled, has his passport confiscated, and is agreed to be ignored. 4 people. 25 years. Not one of them refuted. That is not a conspiracy. There was no meeting. What there was, and this is much worse because it cannot be exposed and does not require any villains, was a professional consensus that the questions were not respectable, enforced through hiring, through supervision, through the tone of voice used at seminars, through the quiet understanding that a young physicist who worked on foundations would not get a job. Which brings us to a man who understood that understanding perfectly and worked on it anyway, in secret, on his own time, for years. John Stuart Bell was born in Belfast on the 28th of July, 1928. His family was working class and Protestant and not academic. His father sold horses at one point. His mother was a dressmaker. Of his siblings, he was the only one who stayed in school past the age of 14, and he only managed that because his mother insisted. He left school at 16 and got a job as a laboratory technician at Queen's University Belfast, cleaning glassware and setting up demonstrations in the physics department. The staff there noticed him. They lent him books and let him attend first-year lectures, and he saved enough to enroll properly a year later. I find this detail hard to get past. The man who wrote the deepest theorem in the foundations of physics in the 20th century got into physics by being the person who washed the equipment. He graduated in 1948, worked at the Atomic Energy Research Establishment at Harwell, took a doctorate at Birmingham, and in 1960 moved to CERN in Geneva, where he stayed for the rest of his life. His job at CERN was accelerator design and particle physics theory. That is what he was paid for. That is what his colleagues knew him for, and he was very good at it. Good enough that a substantial number of physicists knew the name Bell entirely from work on gauge anomalies and had no idea he had anything to do with quantum foundations. Because he did not tell them, he described his interest in the foundations of quantum mechanics as a hobby. He worked on it during a sabbatical year in 1963 and 64 on leave in the United States at Stanford and Brandeis in Wisconsin, and he was careful throughout his career to keep it separate from the work that paid him. He was not being modest. He was managing a professional risk. He said as much later that he would not have advised a young physicist to work on these questions, that it was a good way to not have a career. The man who solved it thought it was too dangerous to recommend. What Bell did in 1964 is so simple in structure that it takes about 10 minutes to walk someone through, and so consequential that 90 years of argument now hinges entirely on it, and I want to do this properly because most explanations skip the step that matters. Take Bohm's version of the EPR setup. A source produces 2 particles in a singlet state, flying apart. Alice has a detector on the left, Bob has one on the right. Each of them can orient their detector along one of several axes, and each measurement returns one of 2 answers. Call them up and down, or plus and minus. The quantum mechanical prediction is straightforward. If Alice and Bob set their detectors to the same angle, their results are always opposite. Perfect anti-correlation. Every time, no exceptions. If they set them at different angles, the correlation weakens in a specific way that depends on the cosine of the angle between them. Now here is Einstein's explanation of that, and it is a good explanation, and this is the crucial thing to understand. It is not a stupid position, It is the obvious position. The particles agreed in advance. When they separated at the source, each one carried a set of instructions. If asked about this axis, answer up. If asked about that axis, answer down. The instructions are opposite for the two particles, which is why they always disagree when measured along the same axis. There is no communication, no influence, nothing travelling. The correlation is established at the source and carried along, exactly like a pair of gloves in two boxes. Open the box in Sydney, find a left glove, and you know instantly that the box in London contains a right one. Nothing has travelled. You have simply learned something that was already true. That is, local hidden variables. That is Einstein's position stated in one paragraph, and until 1964 there was no known way to distinguish it experimentally from quantum mechanics, which is exactly why the field had been able to treat the disagreement as philosophy. Bell's move was to stop arguing about what was in the boxes and start doing arithmetic on the angles. Here is the argument in a form you can check yourself, with no mathematics beyond counting. This is close to the version David Bohm later used for teaching, and it is exact. Give Alice and Bob 3 possible detector settings each. Call them 1, 2, and 3. Physically, they are 3 axes, arranged at 120 degrees to each other in a plane, which is the arrangement that makes the numbers cleanest. On each run, Alice picks one of her 3 settings at random, and Bob picks one of his 3 at random, independently, and each of them writes down up or down. Now suppose Einstein is right. Suppose each particle leaves the source carrying instructions. A complete set of instructions for one particle is an answer to each of the 3 possible questions. Up, down, for example. Or down, up, down. There are 8 possible instruction sets. And because the 2 particles always give opposite answers when Alice and Bob happen to choose the same setting, the second particle's instructions must be the exact complement of the first particle's. That is all forced. No assumptions beyond the 2 Einstein made. The particles carry properties, and what Alice does cannot affect Bob's particle. Now count. There are 9 equally likely combinations of settings, since Alice has 3 choices and Bob has 3. For each of the 8 possible instruction sets, count how often Alice's answer and Bob's answer come out the same. Take an instruction set where all 3 answers are identical. Alice's particle says up to every question, so Bob says down to every question. Alice and Bob's results are opposite in all 9 combinations. They agree 0 times out of 9. Now take any mixed instruction set. Say Alice's particle is up, down, then Bob's is down, up. Work through the 9 combinations. Alice picks setting 1 and gets up. Bob picks setting 3 and gets up, they agree. Alice picks setting 2 and gets up. Bob picks 3 and gets up, they agree. Alice picks 3 and gets down. Bob picks 1 and gets down, they agree. Alice picks 3, Bob picks 2, both down, they agree. That is 4. Every other combination disagrees. 4 out of 9. 6 of the 8 instruction sets are mixed, and every one of them gives 4 out of 9. 2 of them are uniform, and they give 0 out of 9. It does not matter how the source distributes them, how the particles are made, what the hidden variables are, whether they are random or conspiratorial, or drawn from some elaborate underlying theory nobody has invented yet. If the particles carry instructions and Alice cannot influence Bob, then Alice and Bob's results agree at most 4/9 of the time. 4/9 is a hard ceiling. It is not an approximation. It follows from counting. Quantum mechanics predicts 1/2. 1/2 is bigger than 4/9. Not by much, by about 5.5% of the runs. But it is bigger, and it is bigger in a way that no amount of cleverness about hidden variables can close, because the 4/9 did not come from a model, it came from counting the possibilities. That is Bell's theorem. That is the whole thing. A gap of 1/20th between what the world is allowed to do if things are separate and local, and what quantum mechanics says it will do. 29 years, from 1935 to 1964, and nobody noticed that the question could be settled by counting. I need to stop for a moment and be honest about how that makes me feel, because it is the single most disorienting fact in this story. The mathematics required to derive Bell's inequality is accessible to a competent secondary school student. There is no advanced technique in it. Bell did not invent a new formalism or borrow a tool from another field. He counted the possibilities and compared two numbers. Einstein could have done it. Schrodinger could have done it. Von Neumann, who could do essentially anything, could have done it in an afternoon. Bohm was working directly on this in 1952 and did not do it. The reason none of them did it is not that it was hard, it is that nobody was looking, because the profession had agreed the question was not a question. Bell's paper is called On the Einstein-Podolsky-Rosen Paradox. It ran to 6 pages from 195 to 200 in the 3rd issue of the first volume of a journal called Physics, published in November of 1964. You have never heard of that journal. Nobody has. It was founded by Philip Anderson, who would win a Nobel Prize in 1977, and Bernd Mathias, and it had one distinguishing feature. It paid its authors rather than charging them page fees. Bell published there because he was a visitor in the United States on leave from CERN, without institutional funds to cover the page charges that the major American journals levied. He picked the journal that would pay him instead of billing him. The journal folded in 1968 after 4 volumes. It is remembered for exactly one thing, and Bell never received the money. The check went to an address he had already left. The deepest result in the foundations of physics in the 20th century was published in a journal that went out of business by a man who chose it because he was broke and he did not collect the fee. For the first 5 years after publication, the paper was cited almost not at all. Bell went back to CERN and went back to particle physics. He had written the thing that would eventually reorganize the field, and the field did not notice, and he did not push. But this is the point where I have to correct the story that everyone tells about what Bell proved, because the popular version of it is wrong in a way that is not a minor detail. It is wrong in a way that inverts the meaning. The popular version is that Bell proved Einstein wrong and Bohr right, that the argument was settled in favour of Copenhagen, that hidden variables are dead and quantum mechanics is vindicated and we can all go home. Bell did not think that. Bell thought close to the opposite, and he said so repeatedly, in print, for 26 years, and it made almost no difference to how his work was described. What Bell proved is that no theory in which particles carry their properties with them, and local actions have only local effects, can reproduce the predictions of quantum mechanics. That is it. That is the theorem. It rules out a class of theories. It does not establish any particular theory in its place. And crucially, it does not tell you which assumption to drop. Notice that the counting argument above used 2 premises. 1. The particles carry instructions. 2. Alice's choice cannot affect Bob's particle. The conclusion follows from both together. When experiment shows the conclusion is false, at least one premise has to go, and the theorem is entirely silent about which. Bell himself was clear about which one he thought had to go. And it was not the first one. He wrote, in a passage that ought to be printed at the front of every textbook that mentions his name, that his first paper on the subject starts with a summary of the EPR argument from locality to deterministic hidden variables, and that the commentators had almost universally reported that it begins with deterministic hidden variables. He is saying that people have his argument backwards. The determinism was not an assumption he made, it was a conclusion eper derived from locality. Bell's theorem, in his own reading, is an argument that locality fails, full stop, whether or not there are hidden variables. If he is right, then Einstein was not refuted in the way everyone says. Einstein's dilemma from 1935 was either the description is incomplete or something reaches across the gap. Bell removed the first option. He did not remove the second one. He forced it. The absurdity that Einstein put on the table as a reductio became the surviving alternative, and Bell knew exactly what that meant, and it is the reason he remained for the rest of his life. Sympathetic to Bohm, sympathetic to de Broglie, and openly contemptuous of the idea that the foundational problems had been solved. He described the Copenhagen position as an attempt to avoid the question rather than answer it. He described the standard textbook treatment as unprofessional vagueness. When people told him his theorem had vindicated Bohr, he told them they had not read it. Which brings us to the obvious problem. All of this was still theory. Bell had shown that the two positions made different predictions. Nobody had checked which one the world actually obeys, and getting anyone to check turned out to be harder than deriving the theorem. The problem with Bell's inequality as published in 1964 is that it assumes perfect detectors and perfect measurements. Every particle produced gets detected. Every polarizer works exactly. In an actual laboratory in the 1960s, where photon detectors caught a few % of what hit them, the inequality was useless. Real data would violate it for boring reasons that had nothing to do with the nature of reality. That was fixed in 1960, 9 by 4 people whose surnames became the standard abbreviation for the result. John Clauser, Michael Horn, Abner Shimony, and Richard Holt published Proposed Experiment to Test Local Hidden Variable Theories in Physical Review Letters, Volume 23, pages 880 to 884, on the 13th of October. It is universally called SH. What they did was rederive Bell's result in a form that survives contact with reality: inefficient detectors, imperfect polarizers, finite samples. Their version gives a quantity, usually written as S, which cannot exceed 2 for any local hidden variable theory, and which quantum mechanics predicts can reach 2 times the square root of 2, roughly 2.828. Suddenly there was an experiment, and nobody wanted to do it. John Clauser was a graduate student at Columbia, and the story of how he came to this is one I keep returning to, because it inverts the expected morality of the situation. Clauser did not go looking for a way to prove quantum mechanics right. He went looking for a way to prove it wrong. He found Bell's paper in the stacks at the Columbia Library, in a bound volume of a defunct journal nobody read, sometime around 1967. He believed, and said openly, that quantum mechanics was probably going to break somewhere, that the hidden variable program was more likely to be correct, and that Einstein's instincts about the physical world were better than Bohr's. He wanted to be the man who found the crack. His supervisors told him not to. He has described being told by senior figures whose names he has been discreet about and whose identities are not hard to guess that the experiment was a waste of time, that quantum mechanics had been confirmed 1,000 times, and that doing this would destroy his prospects. Richard Feynman reportedly threw him out of his office when he described the proposal. He did it anyway. He wrote to Bell, to Bohm, and to de Broglie in 1969, asking whether anyone had tested it. Bell wrote back immediately and with obvious pleasure. It was the first letter he had received about his theorem from anyone proposing to actually do something about it. 5 years after publication, Clauser got a postdoctoral position at Berkeley, ostensibly in radio astronomy, and built the apparatus in his spare time with a graduate student named Stewart Friedman, using equipment scrounged from around the department. The source was a beam of calcium atoms excited by an arc lamp, which decay through a cascade that emits 2 photons in quick succession with correlated polarizations. The result was published in Physical Review Letters, Volume 28, page 938, on the 3rd of April, 1972. 200 hours of data collection. The measured parameter came out at 0.300 plus or minus 0.008 against a local hidden variable limit of 0.301 plus or minus 0.007. 5 standard deviations of violation. In agreement with quantum mechanics, in violation of the inequality, and in flat contradiction of what the experimenter had been hoping to find. Clauser has described this as the most disappointing result of his career. He had built the machine to catch quantum mechanics failing, and the machine told him Einstein was wrong. He did not stop. And this is where the story gets more complicated than the triumphant version allows, because in 1973 the experiment was repeated and it gave the opposite answer. Richard Holt, the H in Ch, was working at Harvard with Frank Pipkin. They used a mercury cascade rather than calcium, and their result agreed with local hidden variables. Their data satisfied the inequality that Friedman and Clauser had violated. 2 experiments. Opposite conclusions, and here is the part that matters. Holt and Pipkin never published theirs. The result appears in Holt's doctoral thesis in 1973 and nowhere else. They did not believe it. They suspected a systematic error in their apparatus, something to do with stress birefringence in the glass of the vacuum envelope distorting the polarizations, and rather than publish a result they thought was wrong, they held it back. I want to be careful about how that is characterized, because it can be told as a scandal, and it is not one. They had a physical reason to doubt their own data. Sitting on a result you believe is an artifact is defensible and arguably correct. Clauser himself went and repeated the mercury version, published in Physical Review Letters, volume 36, page 1223, in 1976, and got a violation, and the Harvard result was eventually understood as the artifact they suspected. But for 3 years, from 1973 to 1976, the experimental record on the deepest question in physics consisted of 2 experiments that disagreed with each other, and only one of them was in the literature. If you were a physicist in 1974, the honest position was that nobody knew. That is a version of this history you will almost never hear, because it interrupts the clean arc from Einstein's error to Bell's theorem to experimental vindication. Real experimental physics has failed replications and unpublished contradictions, and 3-year periods where the answer flips, depending on which laboratory you trust. Pretending otherwise is how you produce an audience that cannot tell the difference between a settled result and a press release. The result was settled by a French graduate student who read Bell's paper in 1974 and decided to build his career on it, which everyone told him was suicide. Alain Aspect went to see Bell at CERN before starting. He described his proposed experiment. Bell's first question was not about the physics. It was whether Aspect had a permanent position. Aspect said he did, a junior teaching post that could not be taken away from him. Bell said that in that case it might be safe for him to do it. That exchange is the professional culture of foundational physics in 1975 in 2 sentences. The first question the field's most respected theorist asks about a proposed experiment is whether the experimenter is protected from being fired for doing it. Aspect spent about 8 years on this at the Institut d'Optique in Orsay, south of Paris. He built 3 experiments of increasing sophistication, and the third one, is the one that matters, because it attacked the objection that everyone knew about and nobody had addressed. Here is the objection. In the Friedman and Clauser setup, the orientations of the two polarizers were fixed for the whole run. They were set before the photons were emitted, and they stayed there, which means that in principle, some influence could travel from one side of the apparatus to the other at or below the speed of light, carrying information about the settings and coordinate the results. Nothing in the experiment prevented it. The settings had been sitting there, in the same room, for hours. That is the locality loophole. It is not a serious physical proposal. Nobody thinks the polarizers were whispering to each other. But it is a logical gap, and Bell's theorem is a logical argument, and a logical gap in a logical argument is a hole. Aspect's solution was to change the settings while the photons were in flight. The paper is Experimental Test of Bell's Inequalities Using Time-Varying Analysis by Aspect, Jean Dalibard and Gerard Roger, in Physical Review Letters, Volume 49, page 1804, published on the 20th of December, 1982. The apparatus used acousto-optical switches, standing ultrasonic waves in water, oscillating at close to 50 MHz, which deflected each photon into one of two paths leading to differently oriented polarizers. The switching happened on a timescale of about 10 nanoseconds. The two ends of the apparatus were roughly 6 meters from the source on each side, 12 meters or so end to end, which means light takes about 40 nanoseconds to cross it. 10 nanoseconds against 40. The setting on Alice's side changed 4 times over in the interval it would take any signal, travelling at the speed of light. To reach Bob's side and tell it what had happened, the violation came in at 5 standard deviations, in agreement with quantum mechanics, and now the honesty that this audience deserves, and that popular accounts of Aspect almost never provide. The switching was not random, it was quasi-periodic. The ultrasonic standing waves oscillated at a fixed frequency, and the two switches ran at slightly different frequencies so that their relative phase drifted, which makes the settings effectively uncorrelated, but does not make them unpredictable. A sufficiently determined local model, given the deterministic oscillation of the switches, could in principle have anticipated the settings. Aspect knew this. He said so in the paper. He described it as a first step towards closing the loophole rather than as closing it. The 1982 experiment is described in 1,000 places as the experiment that proved Einstein wrong and closed the locality loophole. It did not close it. It made the escape route absurd. There is a difference, and the difference is 33 more years of work, which is where this stops being a story about physics and becomes a story about how far human beings will go to close a gap in an argument. There were 3 gaps, and everyone working on this knew all 3 of them by name. The first is the locality loophole, which Aspect had wounded but not killed. If any signal can travel from one measurement to the other, at light speed or slower during the relevant interval, the correlations have a mundane explanation. The second is the detection loophole, sometimes called fair sampling, and in the 1970s and 80s it was by far the more serious problem, though it got a fraction of the attention. Photon detectors in Aspect's era caught a small percentage of the photons that reached them, which means the dataset is not the set of all pairs produced, it is the set of pairs that happen to be detected. And if the probability of being detected depends in some subtle way on the hidden variables the particle is carrying, then the sample is biased. And a local theory can reproduce an apparent violation without violating anything. That sounds like a technicality. It is not. It is possible to write down explicit local hidden variable models that reproduce every result of every experiment before about 2001, purely by exploiting detection efficiency. They are contrived, and nobody believes them. They are also not refuted by the data. The third is the freedom of choice loophole, and it is the one that does not go away. Bell's argument requires that the settings Alice and Bob choose are independent of the hidden variables in the particles. If the choice of setting and the state of the particle share some common cause somewhere in their past, the argument collapses. Not because anything travels, because the correlation was arranged. The extreme form of that is called superdeterminism, and I will come back to it, because it is the one door nobody has ever managed to shut, and the reason it stays open is not experimental. Closing the first two at once turned out to require 33 years and 3 separate laboratories, and all 3 of them did it in the same year, 2015. The first was in Delft in the Netherlands, and it was the hardest and the most elegant. Bas Henson, Ronald Hansen and their group published Loophole Free Bell Inequality Violation using electron spins separated by 1.3 kilometers in Nature, volume 526, pages 682 to 686, on the 21st of October 2015. They did not use photons as the measured objects. They used electron spins trapped in nitrogen vacancy centers in diamond, which are point defects in the crystal lattice, where a nitrogen atom sits next to a missing carbon. An electron spin trapped in that defect can be read out with essentially 100% efficiency, which annihilates the detection loophole. There is no sampling, because nothing is missed. The problem is that you cannot entangle 2 electrons in 2 separate diamonds 1.3 kilometers apart by shining a light at them. They used entanglement swapping instead. Each diamond emits a photon entangled with its own local electron spin. Both photons travel to a station in the middle, where they are made to interfere and are measured jointly. When the middle station registers the right kind of coincidence, the 2 distant electron spins, which have never interacted and never been anywhere near each other, are left entangled. That is worth stopping on. 2 electrons in 2 separate crystals, over a kilometer apart, are made to share a state by measuring 2 photons somewhere else. Neither electron has ever been within a kilometer of the other. They have no common past in any ordinary sense. And after the middle station clicks, they are correlated in a way that cannot be explained by anything either of them carried. The 2 diamond stations were on the Delft University campus, 1.3 kilometers apart, far enough that a light speed signal could not cross between them during a measurement. The result was 245 successful trials gathered over roughly 220 hours of running, because the success rate for the entanglement swapping was brutally low. S came out at 2.42 plus or minus 0.20 against the local limit of 2. The probability that a local realistic model could produce a violation at least that large came out at 0.039. That is about 1 chance in 26. And that is the first loophole free Bell test in history. I want you to notice how weak that number is. 1 in 26. In particle physics, 1 in 26 would not be a result. It would be a reason to keep running the machine. The most important experiment in the foundations of physics, the first one to close every experimental gap simultaneously, produced a statistical confidence that in any other subfield would be considered an interesting hint. That is how hard this is to do properly. Within 2 months it was crushed, twice, by 2 groups using photons and a new generation of detectors. Marissa Justina and Anton Zeilinger's group in Vienna published in Physical Review Letters, volume 115, article 250401, in December of 2015. They used superconducting transition edge sensors, detectors cooled to a fraction of a degree above absolute zero, with efficiencies high enough to close the detection loophole for photons for the first time. 3,502,784,150 valid trials. The probability of their results arising under local realism came out at 3.7, 4 times 10 to the minus 31. That is 11.5 standard deviations. 10 to the minus 31 is not a number that means anything to a human being, so here is a comparison that does. If you had a fair coin and you flipped it 100 times, the chance of getting all 100 heads is roughly 10 to the minus 30. The Vienna result is less likely than that under local realism by another factor of 10. The third came from the National Institute of Standards and Technology in Boulder, Colorado. Lyndon Shalm and colleagues, strong loophole free test of local realism, in the same journal and the same issue, article 250402. Their announcement put the maximum probability of local realism producing their data at about 1 in 170 million. 3 experiments. 3 continents. 3 completely different physical systems, diamond defects and photon pairs and superconducting sensors, with different failure modes and different systematics. All 3 published within 9 weeks of each other. All 3 agreeing. 80 years after Podolsky drafted the paper, the experimental question was finished, except that it was not, because the third loophole was still open, and the third loophole is not a technical problem. Bell's argument requires that the settings be independent of the particles. In every experiment up to 2015, the settings were generated by devices in the laboratory. Random number generators, quantum or classical, sitting a few meters from the source. Made of matter that had been in causal contact with the source for the entire history of the apparatus. If you want to be maximally paranoid, and at this stage of the argument maximal paranoia was the only rigorous position left, then the settings might have been correlated with the hidden variables through some shared cause in the recent past. The response to this was 2 of the strangest experiments ever performed, and the first one is the one I find genuinely moving. On the 30th of November, 2016, over a 12-hour period, more than 100,000 people around the world played a video game. The game asked them to press keys as unpredictably as they could. Every keystroke produced a bit. Those bits were streamed live at over 1,000 per second to 13 experiments in 12 laboratories on 5 continents, where they were used to choose the measurement settings in Bell tests running in real time. 97,347,490 human choices, made by 100,000 people who mostly had no idea what a Bell inequality is. Feeding into an argument that Einstein started in 1935. The results were published in Nature, volume 557, pages 212 to 216, in May of 2018. The paper is called Challenging Local Realism with Human Choices. The inequalities were violated. The reasoning behind it is worth stating precisely, because it is doing something philosophically odd. The idea is that if human decisions have any component that is not determined by the prior state of the universe, then using human decisions as the settings removes the correlation between settings and hidden variables. The experiment is not proving free will, it is conditionally invoking it. If you have any, the loophole is closed. If you do not, it is not. That is where this argument had arrived by 2018. To rule out one remaining explanation of a correlation between 2 photons, physicists had to build an apparatus whose validity depends on whether human beings have free will. The other experiment reached in the opposite direction. Dominic Rauch, Zeilinger, David Kaiser, Alan Guth and their collaborators published Cosmic Bell Test using random measurement settings from high redshift quasars in Physical Review Letters, volume 121, article 080403, on the 20th of August, 2018. This is the experiment I opened with. The settings were determined by the colours of individual photons arriving from 2 quasars. one whose light was emitted about 7.8 billion years ago, and one about 12.2 billion. The logic is that if the setting is determined by light emitted 12.2 billion years ago, then any conspiracy between the setting and the particles has to have been arranged before that light was emitted. The common cause has to sit further back than the emission event, which pushes the required conspiracy back into the first 15% of the age of the universe. The violation came in at 9.3 standard deviations. The authors calculate that they excluded local realist explanations from around 96% of the space-time volume of the experiment's past light cone. 96%. Not all of it. There is a residual 4% back near the beginning where the correlation could in principle have been arranged. And there is no experiment, in principle, that can ever eliminate that. Push the settings back to the earliest light in the universe, and the conspiracy retreats to before that light. Superdeterminism is not refutable by experiment, because any experiment you perform is made of matter with a past, and the hypothesis is precisely that the past arranged it. It is not refutable. It is also, and I want to be exact about this rather than dismissive, taken seriously by a small number of serious physicists, most prominently Gerard Hooft, who won the Nobel Prize in 1999 and who has argued for a superdeterministic underpinning of quantum mechanics for over a decade. The reason most physicists reject it is not evidence. It is that if the initial conditions of the universe are correlated with the settings of every experiment ever performed, then the practice of doing science, which assumes you can choose what to measure, has no foundation. Superdeterminism is rejected because accepting it would make the rejection meaningless. That is not a refutation. That is a decision about what kind of universe we are willing to work in. On the 4th of October, 2022, the Royal Swedish Academy of Sciences announced that the Nobel Prize in Physics would be shared equally between Alain Aspect, John Clauser, and Anton Zeilinger. The citation reads, "For experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. 87 years after the paper, 58 years after the theorem, 50 years after Friedman and Clauser ran 200 hours of calcium cascades in a scrounged laboratory at Berkeley while being told it would end their careers. Clauser was 79. He had spent the intervening decades outside the mainstream of physics, doing contract work, holding no permanent professorship, having been correct about the most important experiment of his generation, and having paid for it in exactly the way his supervisors warned him he would. There is a name missing from that citation. John Bell died on the 1st of October, 1990, in Geneva, of a cerebral hemorrhage. He was 62 years old. It was sudden. He had been at work. He had received the Dirac Medal in 1988, the Hughes Medal in 1989, the Heinemann Prize in 1989. His biographer Andrew Whittaker has written that he was nominated for the Nobel Prize, and that had he lived longer he would very likely have received it. I have to flag the epistemic status of that because it matters, and because the audience for this deserves the flag rather than the flourish. Nobel nomination archives are sealed for 50 years. The nominations for 1990 will not be public until 2041. Whittaker's statement is well informed and comes from someone with access to Bell's circle, and it is not independently verifiable, and it will not be verifiable for another 15 years. What is verifiable is that the prize is not awarded posthumously, that Bell died in 1990, and that the prize for his theorem was given in 2022. 32 years. He missed it by 32 years. The man who found the crack, who was a laboratory technician at 16, who published in a journal that went bankrupt, who never got paid, who told young physicists not to work on this because it would ruin them, died at his desk in Geneva 3 decades before the field gave its highest honour to the experiments testing his theorem. I said I would come back to Podolsky, and this is the point to do it, because the man whose name is on the paper and who wrote every word of it has a second story that almost nobody knows. Boris Podolsky was born in Taganrog in southern Russia in 1896 into a poor Jewish family. He emigrated to the United States in 1913 at 17 with almost nothing. He worked as a labourer. He put himself through the University of Southern California, took a doctorate at Caltech in 1928 under Paul Epstein, worked with Dirac in Cambridge and with Fock in Leningrad, and arrived at the Institute for Advanced Study in the early 1930s. That is a serious career. That is a man who crossed an ocean at 17 with nothing and ended up in a room with Albert Einstein. And then he leaked to the New York Times, and it ended. But in 2009, 3 historians published a book called Spies, based on Alexander Vassiliev's notebooks. Vassiliev was a former KGB officer who was permitted, in the 1990s, to transcribe extensive material from Soviet intelligence archives, and who then got the notebooks out of Russia. The book is by John Earl Haynes, Harvey Clare, and Vassiliev himself. In it, they identify a Soviet source code named Quantum in Russian Kvant as Boris Podolsky. The account is this. In early 1942, an émigré physicist approached Soviet officials offering to work in the Soviet Union on uranium. In a meeting at the Soviet embassy in Washington in 1943, he passed over material on gaseous diffusion, the method of separating uranium isotopes, and was paid $300. The material was of limited value. Some of the equations involved were elementary, essentially Graham's law of diffusion, which had been known since 1848. The Soviets concluded he was not a productive source and dropped him. Now here is the part where I need you to hold 2 things at once. The historians who published this describe their own evidence as somewhat indirect. The identification of Quantum as Podolsky is an inference drawn from the details in Vassiliev's notes, matched against biographical facts. It is not a signed document. It is not a photograph. It is an argument from circumstantial fit, made by serious scholars, published in a serious book, and it is contested. Podolsky died on the 28th of November, 1966. 43 years before that book appeared, he never had the chance to answer it. I am telling you because it is documented, and because the alternative, leaving it out, is the same editorial instinct that removes Podolsky's authorship from the story of the paper he wrote. But the correct epistemic status of the claim is contested, resting on indirect archival evidence. And anyone who tells you flatly that the author of the EPR paper was a Soviet spy is going further than the evidence supports. What I will say is this. The man who wrote the most important critique of quantum mechanics in history, whose reward for it was to lose Einstein's friendship over a newspaper leak, spent the last 30 years of his life at a small university in Cincinnati, largely forgotten by the field, and there is a plausible archival case that somewhere in the middle of that he sold elementary diffusion equations to a foreign government for $300. That is not a triumphant arc. It is not a tragic one either. It is a small, human, slightly squalid life attached to one of the largest ideas of the century, and the reason it never appears in the popular telling is that it does not fit any of the shapes we like our science stories to have. Nathan Rosen's life took a different course entirely, and I have been saving him. Rosen was born in Brooklyn on the 22nd of March, 1909. He took his doctorate at MIT in 1932 and came to Princeton as Einstein's assistant, working with him from 1934 to 1936. He was 26 years old when the EPR paper was published. He did the calculations. He moved to the Soviet Union for 2 years, then back to the United States, and in 1952 he emigrated to Israel and joined the Technion in Haifa, where he built the physics department essentially from nothing. He served as president of Ben Gurion University. He helped found the Israel Academy of Sciences. He died in Haifa on the 18th of December, 1995, at 86. He is the only one of the three who lived long enough to see aspects result. 13 years long enough. And Rosen is the reason this story has one more turn in it, because of the other paper. 6 weeks after the entanglement paper, on the 1st of July 1935, Physical Review published The Particle Problem in the General Theory of Relativity by Einstein and Rosen. Volume 48, pages 73 to 77. It is a paper about general relativity, not quantum mechanics. Einstein and Rosen were trying to construct a model of an elementary particle out of pure space-time geometry, a way of getting matter out of the field equations without putting matter in by hand. What they found, in the mathematics of the Schwarzschild solution, was a structure that connects two regions of space-time through a throat. Two mouths, one bridge. The Einstein-Rosen bridge, what everyone now calls a wormhole, a term John Wheeler coined about 20 years later. The particle model did not work. The paper is remembered for the incidental structure it described rather than for what it set out to do. Two papers. 1935, the same journal. Einstein and Rosen on both. One says that two separated systems cannot be secretly connected. The other describes a geometry in which two distant places are directly connected through a throat that does not exist in the space between them. In 2013, Juan Maldacena and Leonard Susskind published a paper in Fortschritt der Physik, volume 61, pages 781 to 811, called Cool Horizons for Entangled Black Holes. The conjecture in it is usually written as 3 letters, an equals sign, and 3 more letters. ER equals EPR. They propose that the two papers Einstein published in 1935 are describing the same thing. The argument comes out of black hole physics, rather than from anything Einstein was thinking about. If you take two black holes and entangle them maximally, particle by particle, the resulting geometry in the mathematics has an Einstein-Rosen bridge connecting their interiors. That much is a calculation, and it is not seriously disputed. Maldacena and Suskind's move was to run it backwards and generalize. If maximal entanglement between two black holes produces a wormhole, then perhaps entanglement between any two systems is a wormhole, a very small one, a Planck-scale throat, not traversable, not something you could send anything through, but a genuine geometric connection rather than a mysterious correlation. On that reading, the two particles in an EPR pair are not connected by a signal, because there is no signal. They are not connected by an influence, because there is no influence. They are connected by geometry. There is a bridge, and the reason nothing travels along it is that the two ends are, in some sense, that the mathematics can express and ordinary language cannot, not actually at two different places. I want to state clearly what this is and is not. ER equals EPR is a conjecture. It is not established. It is taken seriously by a substantial part of the quantum gravity community. It has generated an enormous literature. It connects to work on holography and on the black hole information problem, and it is entirely possible that in 20 years it will be regarded as a productive metaphor that turned out to be the wrong picture. I am not telling you this is true. I am telling you it is on the table in respectable journals proposed by two of the most serious people in the field, and I am telling you because of the shape of it. Einstein spent 20 years arguing that quantum mechanics could not be complete because it implied a connection between separated systems, and that such a connection was unacceptable. The leading contemporary proposal for what that connection is says it is the other thing Einstein discovered in the same year, in the same journal, with the same collaborator, while trying to do something else entirely. He wrote down the objection and the answer within 6 weeks of each other and did not notice. That is either the most beautiful coincidence in the history of physics, or an indication that he was circling something real from 2 directions and could see it from neither. Now, everything I have described so far is about whether the correlations are real and what could explain them. There is a separate question, and it is the one where most popular coverage of this subject goes completely off the rails, and I need to shut it down before we go any further, because the whole final movement of this depends on getting it right. Entanglement cannot send a message. Ever. At any speed. Under any circumstances. This is not a practical limitation. It is not an engineering problem that a better apparatus will solve. It is a theorem. It is called the no communication theorem, or the no signaling theorem, and it was formalized by Philippe Eberhard in a paper in Il Nuovo Cimento B, volume 46 in 1978, and independently by Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber in Lettere al Nuovo Cimento. Volume 27 in 1980. Here is why it works. When Alice measures her particle, she gets a random result. Up or down, 50-50, and she cannot control which. Nothing she does can bias it. Her results are noise. Bob, looking at his own particle, also gets noise. Whatever Alice does, whatever setting she chooses, whether she measures at all, the statistics Bob sees on his side are identical. Perfectly, provably identical. His marginal distribution does not depend on anything happening at her end. The correlation only appears when Alice and Bob compare their lists. And to compare their lists, one of them has to send the other a copy, and that copy travels by telephone or radio or courier, all of which are limited by the speed of light. 2 identical sequences of random noise generated in 2 places which turn out to match when you lay them side by side. Neither person can put anything into their sequence. Neither person can read anything out of the other person's. The information exists only in the comparison, and the comparison is slow. That is the strangest possible arrangement. The universe permits a correlation that no local mechanism can explain, and then guarantees, with mathematical exactness, that you cannot use it for anything. I find that more disturbing than a signal would be. A signal would be a phenomenon. You could study it, measure its speed, look for a medium. This is a connection that is real enough to violate an inequality by 11.5 standard deviations and useless enough that you cannot send a single bit through it. Whatever is going on, it is arranged so that you cannot catch it in the act. Which brings us to the last part, and the part where I have to survey the options and be honest that all of them are unacceptable. Bell's theorem, plus the experiments, tells you that at least one of the assumptions in the argument is false. It does not tell you which. The field has therefore split into camps, and each camp has picked something to give up. What I want you to watch for is not which one is right. It is what happens when you lay them side by side. Copenhagen, in its modern forms, gives up the idea that the theory describes what is there. Quantum mechanics is a calculus for predicting measurement outcomes, and asking what is happening between measurements is not a physics question. The correlation does not need an explanation because there is nothing to explain. There are only outcomes. The many worlds interpretation, from Hugh Everett's 1957 thesis, gives up the idea that measurements have single outcomes. Alice's measurement does not produce a result. It splits her into branches, one for each result. There is no non-locality because there is no fact about what Bob will find until the two of them come into contact and their branches align. It is local, and it purchases that locality by asserting that everything that can happen does happen, in parallel forever, including every version of you that made a different choice this morning. Bohmian mechanics gives up locality outright and admits it. Particles have positions, the wave function guides them, and the guidance is instantaneous across any distance. It is the only major interpretation that answers the question I asked at the start with a straight face. What is between them? A wave in configuration space, and it is real, and it does not live in the space you live in. Objective collapse theories, like the Ghirardi-Rimini-Weber model, give up the exactness of the Schrodinger equation. Wave functions really do collapse spontaneously at random, with a probability that scales with the size of the system, which is why a particle stays in superposition and a cat does not. This one is testable, it makes predictions that differ from standard quantum mechanics, and experiments have been narrowing its parameter space for 30 years. Cubism gives up the idea that the wave function describes the world at all. It describes an agent's beliefs. The correlation is not out there, it is in the relationship between what you know and what you will find. Retrocausal accounts give up the direction of time. The measurement settings influence the past state of the particles. There is no faster than light influence, because the influence goes backwards along the light cone rather than sideways across it. Superdeterminism gives up the independence of your choices from the state of the universe. 7 positions. They disagree about everything. They disagree about whether the wave function is real, whether particles have positions, whether there is one world or many, whether the future can reach the past, whether you have any freedom in what you measure. And here is the thing they all agree on. Every single one of them purchases its consistency by abandoning the idea that the world is made of separate things with their own separate states. Copenhagen does it by refusing to say what the separate things are doing. Many worlds does it by making the separateness a local appearance inside a single undivided universal wave function. Bohm does it by making the guiding field a single object defined over all the particles at once. Collapse theories do it by making the collapse a global event. Cubism does it by moving the description into the agent. Retrocausality does it by connecting the ends of the experiment through time instead of space. Superdeterminism does it by tying every part of the universe to a common past state. Not one of them lets you keep it. Not one of them, in 91 years, has found a way to have the correlations and also have a world made of independent pieces. That was Einstein's assumption. The one he defended in the Dialectica paper, the one Howard identified as his real position, the one nobody talks about, because everyone is busy talking about dice. He said that if you cannot maintain the independent existence of spatially separated things, then physics as we understand it is impossible. Nobody has maintained it. Every root out of Bell's theorem sacrifices exactly the thing he said could not be sacrificed. He was not wrong about the stakes. He was wrong about which way the world would go. There is a live and genuinely unresolved argument about how to describe that, and it is worth walking into because it is where the honest disagreement actually sits, as opposed to where the popular accounts pretend it sits. The standard textbook formulation says that Bell tests rule out local realism, 2 words, joined, treated as a package, and a serious group of philosophers of physics has spent 20 years arguing that this phrasing is not merely imprecise, but historically manufactured and actively misleading. Tim Maudlin has made this case as forcefully as anyone. In a paper called What Bell Did, in the Journal of Physics A, volume 47, in 2014, he argues that what Bell proved, and what theoretical physics has still not absorbed, is that the physical world itself is non-local. Not that realism fails, not that we must choose between 2 options. Locality, on his reading, is the only casualty because the determinism in Bell's argument was never an assumption. It was derived by EP from locality plus the perfect correlations. Travis Norson has argued the same thing from a different direction. In a paper called Against Realism, in Foundations of Physics in 2007, where he takes apart the word realism as it is used in this literature and shows that it does not have a stable meaning across the papers that use it. Nicholas Gissin, who has done as much experimental work on this as anyone alive, has written that non-local correlations seem to emerge from outside spacetime, not from far away, from outside. He has written flatly that nature is non-local, and there are people who think all of that is overreach. Marek Zukowski and Marian Kupczynski have argued that the non-localist reading imports assumptions that Bell's mathematics does not require, and that contextuality, the fact that measurement outcomes depend on the full experimental arrangement, is sufficient to account for the results without any spooky geometry. I am not going to pretend to adjudicate that. What I want you to see is the situation itself. 91 years after the paper, 60 2 years after the theorem, 11 years after every experimental loophole worth closing was closed. And the most fundamental question, which is what the experiments actually tell us about the world, has no consensus answer among the people best equipped to answer it. There have been surveys of this, polls taken at foundations conferences asking working physicists which interpretation they favour. The results are always the same shape. No option gets a majority. Copenhagen leads with something like 40%, Many Worlds gets a substantial minority, everything else splits the rest, and a meaningful number of respondents decline to answer or say the question is not well posed. Imagine that in any other field. Imagine a survey of structural engineers in which 40% believe bridges stand up because of compression, 30% because of parallel universes, and 15% think the question is meaningless. I am not saying physics is broken. The predictions work. The predictions work better than anything else humans have ever built. Quantum electrodynamics agrees with measurement to 12 significant figures, which is the most precisely confirmed prediction in the history of science. I am saying that a field which can predict the magnetic moment of the electron to 12 decimal places cannot tell you what happens between two entangled particles, and has organised its professional culture so that not being able to tell you is not embarrassing. That is the abdication. Not a cover-up. Nobody is hiding anything. Every paper I have cited is public, most of them are free to download, and the physicists involved will talk about this at length if you ask them at the right moment. The abdication is that it is not taught. Open an undergraduate quantum mechanics textbook, one of the standard ones, and see how many pages Bell's theorem gets. In many of them the answer is none. In the ones that include it, it is frequently in a final chapter after the material that will be examined, marked as optional. Generations of physicists have completed doctorates without ever working through the argument I walked you through earlier, the one that takes 10 minutes and requires only counting. The most important theorem about the nature of physical reality produced in the 20th century is optional coursework. Meanwhile, the thing Einstein said was absurd has been turned into hardware. In 2017, a Chinese satellite called Messius, orbiting at about 500 kilometers, distributed entangled photon pairs to 2 ground stations in Dillinga and Lijiang, 1,203 kilometers apart. The results were published in Science, volume 356, pages 1140 to 1144, by Wan Yin, Jian Wei Pan, and their group. The entanglement survived the trip through the atmosphere and out and back down, and the Bell inequality was violated over that distance. Quantum key distribution, which uses this to generate encryption keys that cannot be intercepted without detection, is a commercial product. You can buy it. Banks use it. The security guarantee rests directly on the fact that entangled correlations cannot be explained by anything the particles carried with them, because if they could, someone could have copied the carried thing. The The commercial viability of a security technology depends on Einstein having been wrong in 1935. Quantum teleportation, proposed by Charles Bennett and 5 colleagues in 1993 and first demonstrated by Zeilinger's group in 1997, transfers the complete quantum state of one particle to another using an entangled pair plus a classical message. The name is unfortunate and has caused 25 years of confusion. Nothing is transported. The state is reconstructed at the far end, and it cannot be reconstructed without the classical message, which travels at or below light speed, which is the no communication theorem enforcing itself again. But the state that arrives is not a copy. The original is destroyed in the process. There is a theorem about that too, the no cloning theorem from 1982, which says you cannot duplicate an unknown quantum state. And the way that theorem came into existence is the funniest and most revealing thing in this entire history. So I am going to take a detour. Because it tells you something about who was keeping this question alive during the years the profession had abandoned it. By the mid-1970s, serious institutional physics had almost entirely vacated the foundations of quantum mechanics. What filled the vacuum, in Berkeley, was a group of physicists with doctorates and no prospects who met on Friday afternoons at the Lawrence Berkeley Laboratory and called themselves the Fundamental Physics Group. The historian David Kaiser wrote a book about them called How the Hippies Saved Physics, and the title is a joke that is about 80% accurate. These were not cranks. Elizabeth Rauscher and George Wiseman founded it, Jack Sarfati and Fred Alan Wolfe and Nick Herbert were regulars, and John Clauser was in and out of it. They had real training. What they did not have was jobs, because the academic market had collapsed after the Apollo program wound down and defense funding contracted, and there were vastly more physics doctorates than positions. They were unemployable and interested in Bell's theorem, which were closely related conditions. Some of their funding came from the Esalen Institute in Big Sur, which is a retreat centre associated with the human potential movement, and some of it came from an eccentric millionaire, and some of their meetings involved discussion of telepathy. All of that is true, and all of it is used to dismiss them. What is also true is that this group spent the late 1970s obsessively working through the implications of entanglement at a moment when respectable departments would not touch it, and that the modern field of quantum information owes them a debt that took 30 years to acknowledge. Nick Herbert wanted to build a faster-than-light telegraph. He was serious about it. In 1981, he circulated a proposal called FLASH, an acronym for First Laser Amplified Superluminal Hookup. The idea was to take one half of an entangled pair, run it through a laser gain medium to produce many copies of its state, and measure the copies statistically. If you could copy an unknown quantum state, you could determine what basis the distant partner had been measured in. And that would be a signal, and the no communication theorem would be dead, and so would relativity. He submitted it to Foundations of Physics. It went to Asher Perez as a referee. Perez recommended publication. He said afterwards in print that he knew the paper was wrong. He could not immediately identify the error, and he judged that publishing it would provoke somebody to find the flaw, and that finding the flaw would be worth more than quietly rejecting a mistaken paper. That is the single most intellectually honest act of refereeing I am aware of, and it worked. Within months, Wojciech Zurek and William Wouters published a paper in Nature, volume 299, pages 802 to 803, in 1982. The title is A Single Quantum Cannot Be Cloned. Dennis Dierks published the same result independently in Physics Letters A in the same year. The reason Herbert's telegraph fails is that amplification introduces exactly enough noise to destroy the information, always, unavoidably, and the amount of noise is precisely what is required to prevent signaling. The universe does not merely decline to let you send a message. It has a specific mechanism for making sure you cannot, and that mechanism turns out to be one of the foundational results of quantum information theory. The no-cloning theorem is the backbone of quantum cryptography. It is why an eavesdropper cannot copy a key in transit. It exists because an unemployed physicist funded partly by a spiritual retreat center tried to break relativity, and a referee let him try. Every secure quantum communication link in operation today rests on a theorem that was proved to explain why a hippie's faster-than-light telegraph would not work. What arrives at the far end, then, is not a copy of the original. It is the original, in a new location, with nothing having crossed the gap except two classical bits and whatever entanglement is. Sit with that phrasing for a moment, because it is precise and it is not a metaphor. The thing that made that particular particle, has moved from one place to another. The route it took is not describable in terms of anything travelling through the space in between. Every one of these technologies works. Every one is deployed. And not one of them requires anybody to be able to say what entanglement is. That is the final form of the abdication, and it is the most effective one. Because it is not suppression at all. It is success. You do not need to answer a question that has stopped costing you anything. Einstein would have found that unbearable. He said as much, repeatedly, in the language of a man watching a discipline choose utility over understanding. He wrote to Schrodinger that the Copenhagen position functions as a kind of soft pillow, something a true believer could rest on and not be easily woken from. The exact wording of that passage is one I would want to check against the archive before putting it in anyone's mouth, and the sentiment is unmistakable across dozens of letters. He was not complaining that the theory was wrong, he was complaining that it was comfortable. And here is the thing I keep coming back to, the thing I have not been able to put down since I started reading the primary material for this. Einstein's argument was correct, not his conclusion, his argument. Go back to the structure of it. He said, either the description is incomplete or something reaches across the gap. He was certain the second option was absurd, so he concluded the first. The experiments have shown that the first option is not available in any local form, which leaves the second one standing there, exactly where he put it, still absurd, and now mandatory. Every single person who has tried to make quantum mechanics comprehensible in the 91 years since has had to pay Einstein's price. Bohm paid it explicitly. Everett paid it by multiplying worlds. Copenhagen pays it by declining to describe. The retrocausal accounts pay it in the currency of time instead of space. He identified the exact thing that would have to be given up. He was the only person in 1935 who saw clearly what the cost would be. And the entire discipline has spent 9 decades paying that cost, while describing him as the man who did not understand quantum mechanics. There is one more thing, and it is the thing I have been circling since the first minute of this, and I want to give it to you carefully because if I rush it, it will sound like mysticism, and it is not mysticism. It is bookkeeping. Entanglement is not rare. That is the assumption underneath everything, and it is wrong. The way this subject is taught, entanglement sounds like a delicate laboratory condition, something you produce with a beta barium borate crystal and a laser and enormous care, which decoheres within microseconds if anyone breathes near it. Producing usable, measurable, controllable entanglement is difficult. Producing entanglement is not difficult. Producing entanglement is what happens whenever two quantum systems interact. It is the default. It is Schrödinger's characteristic trait, and he chose that word deliberately, because interaction without entanglement is the special case, not the other way around. Every particle that has ever interacted with another particle has become entangled with it. The entanglement then spreads, because the second particle interacts with a third, and the correlations propagate outward and get diluted across the environment until they are practically impossible to detect. That is what decoherence is. Not the destruction of entanglement. It's dispersal. The entanglement does not go away. It becomes unmeasurable, which is a fact about your instruments, not a fact about the world. Follow that back. Every atom in your body was assembled from particles that interacted with other particles. The hydrogen in the water in your cells formed in the first few minutes after the Big Bang, and has been interacting ever since. The carbon and oxygen were made inside stars that died before the sun existed, in interactions that entangled them with everything else in that star. The photons hitting your retina right now interacted with the surface they bounced off, and are now correlated with it, and with you. There is no step in that chain where the correlations stop. There is no boundary in physics where a system becomes genuinely separate from what it interacted with. We draw those boundaries because we have to, because you cannot calculate anything otherwise, and there is nothing in the theory that draws them for us. Hold that thought. Because in a few minutes I am going to tell you what it means for the question we started with, and it is not a metaphor about interconnectedness, and it is not going to make you feel warm. The formal name for this is the universal wave function, and the reason it is uncomfortable is not philosophical. It is that the mathematics has no natural place to stop. Schrödinger's equation is linear. Apply it to a particle, you get a wave function. Apply it to a particle and a detector, you get a joint wave function of both. Apply it to a particle and a detector, and a physicist, and a laboratory and a planet, and the equation does not object. It has no term that says stop here. It has no parameter for how big is too big. Everett noticed this in his thesis in 1957 and drew the obvious conclusion, which is that if the equation applies universally, then there is one wave function for everything and no collapse anywhere. He was 26. Bohr's circle in Copenhagen treated him with a contempt that is documented in the correspondence. Everett left physics entirely, went to work in defense analysis, doing nuclear targeting calculations for the Pentagon, drank heavily, and died of a heart attack at 51 in 1982, the same year Aspect published. His instructions were that his ashes be put in the rubbish. His family followed them. Count again. De Broglie, Hermann, Bohm, Everett, Bell, Clauser, 6 people, across 50 years, every one of whom took the foundational questions seriously, and not one of whom had the career they would have had if they had worked on something else. That is not a coincidence, and it is not a conspiracy. It is what a professional culture does to protect a consensus it cannot defend. And it worked, in the sense that the questions stayed closed for long enough that the technology arrived first. We now build machines that exploit entanglement, sell products whose security depends on it, and award Nobel Prizes for measuring it, while the question of what it is remains exactly where Einstein left it on the 15th of May, 1935, which is where I have to leave you, because there is nowhere else to go. Go back to the question I asked at the start. 2 objects, separated in space, correlated in a way nothing they carried can explain. What is between them? After 91 years, the best available answer is that the question contains a mistake, and the mistake is the word between. Between assumes 2 things and a gap. It assumes that the separation is the primary fact and the correlation is something that has to cross it. Every attempt to explain the correlations by finding something that crosses the gap has failed, and the failures have been definitive, and they have been definitive for 11 years now with every loophole closed. What survives is the other option, that the separation is not the primary fact, that the 2 particles are not 2 things that happen to be correlated, but one thing that is being described by us from 2 locations, because we are built to stand in one place at a time and cannot describe anything any other way. That is what Maldacena and Susskind's conjecture says in the language of geometry. There is no gap, because the two ends are connected by a throat that does not pass through the intervening space. That is what Bohm's guiding wave says in the language of configuration space. There is no gap, because the object doing the guiding is not in space at all. That is what Everett says in the language of branches, and what Copenhagen says by declining to speak. Different vocabularies, same surrender, and once you accept that separation is not fundamental, the thing I asked you to hold 10 minutes ago comes due. The line around you is not drawn by physics. Every particle in your body has interacted, and everything it interacted with it became correlated with, and those correlations were never destroyed. They were spread out into an environment too large and too disordered for anyone to track. The mathematics that describes you as a system does not derive that boundary from anything. We impose it, because a calculation has to have a system and an environment, and the choice of where to put the cut is made by the person doing the calculation. You are a region of a wave function that we have agreed, for practical reasons, to treat as a separate object. That is not poetry. That is the actual status of the boundary in the actual formalism. There is no equation that produces you as a distinct entity. There is only the fact that the correlations between you and everything else are too dilute to measure, and the fact that measuring them is not the same as their not being there. Einstein saw where this went, not the details, not the branches or the throats or the guiding waves, but the shape of it. He said that if the independent existence of spatially separated things could not be maintained, physics as we understand it would be impossible. He meant it as a warning about the theory. It reads better as a prediction about the world. He spent the last 2 decades of his life on unified field theory, working alone on a program that essentially everyone around him regarded as a dead end and a sad way for a great man to finish. He was at the Institute in Princeton, in an office, doing calculations that went nowhere, while the physics he had helped start went off in a direction he refused to follow. On the 17th of April, 1955, his abdominal aortic aneurysm ruptured. He refused surgery. He said he had done his share, that it was time to go, and that he wanted to go elegantly. He was taken to Princeton Hospital, and he asked for his glasses, his notebook, and the draft of a speech he was working on. He spent his last night doing calculations. The pages were with him. They contain equations for the unified theory he never found, and among them are lines of ordinary arithmetic, crossed out, restarted. He died in the early hours of the 18th of April. 27 years later, Alain Aspect switched a polarizer in 10 nanoseconds in a laboratory in Orsay and got a violation at 5 standard deviations, and the option Einstein had put on the table as the obviously absurd one became the only one left standing. 63 years later, a team pointed telescopes at 2 quasars in order to borrow randomness from a universe that was 2 billion years old, because that was the only source of decisions they were willing to trust, and it still was not enough to close the argument completely. 87 years later, 3 men collected a Nobel Prize for the experiments, and John Bell had been dead for 32 of those years, and Boris Podolsky for 56, and Grete Hermann for 38, and David Bohm for 30, and Hugh Everett for 40. And in all that time, through all those experiments, across every laboratory and every satellite and every diamond and every quasar, nobody has been able to say what is happening between the 2 particles. Not because the answer is hidden, because the question is asking about a between that the physics does not contain. Here is where that leaves you. Right now, as you listen to this, the air in the room is exchanging photons with your skin. The molecules in your lungs are colliding with molecules that were in someone else's lungs a week ago. Every one of those interactions is producing correlations that will never be undone. only spread. Nothing in the theory says where you end. The boundary between you and the room is a modelling convenience, adopted because the alternative is a calculation nobody can perform. Einstein wrote 4 pages in 1935 to prove that the world had to be made of separate things, because a world that was not made of separate things could not be described. He was right about that. It cannot be described. 91 years of the best minds in the subject have not described it. What we have instead is a formalism that predicts every measurement to 12 decimal places, while remaining silent about what it is a formalism of. A set of interpretations that disagree about everything except the one thing Einstein cared about, and a professional consensus that this is fine. He was not the man who failed to understand quantum mechanics. He was the man who understood what it would cost, refused to pay it, and was overruled by the universe. The paper he did not write, that he read in print and immediately regretted, that his co-author leaked to a newspaper, and then possibly sold pieces of his career to a foreign intelligence service. That was answered by a reply nobody has ever been able to paraphrase. Is the founding document of the technology now securing bank transfers between continents? And the connection it described, the one he built as a reductio, the ghostly remote action that was supposed to be so obviously impossible that pointing at it would end the argument, is not something that happens between 2 particles. It is what the 2 particles are made of. There is no signal crossing the gap. There never was. There is no gap. You have spent your entire life believing that you are here and that other things are elsewhere, that the distance between you and the wall is a real feature of the world, that separation is what space is for. Every experiment run since 1972 says that the correlations do not care about that distance and never did. The particles in your hand are not in your hand in the way you think they are. Nobody knows what they are in instead. And the man who first noticed, who spent 20 years trying to get someone to take the problem seriously, who was told at every turn that the matter had been settled by a reply he found incomprehensible, died in a hospital bed in New Jersey in the small hours of a Monday morning, with a pencil, working on the wrong equations, still trying to put the world back into pieces.